Parallel transport of vectors, 2. Let us derive the parallel transport of vectors in curved space. In flat Euclidean space, the magnitude of a vector does not change under parallel transport. This may seem natural and obvious, but it is in fact the definition in flat space. Since the basis is the same throughout the entire space, the components of any vector are expressed in exactly the same way everywhere. What about in curved space? Let us consider the exact same vector. At a point x, the components of the vector are determined by the basis at that point. At a nearby point, however, the basis is already different, so the components take on entirely different values. This means that even comparing the same vector at two different points is not straightforward. A vector is an invariant, independent of the choice of coordinates. Even when the basis differs and the components are expressed differently, the vector must still be represented with the same magnitude. Deriving the mathematical expression that satisfies this condition is the goal of parallel transport in curved space. First, let us clarify the setup of the vector an in Euclidean space. A vector at a point in three-dimensional space is expressed as Note: in Euclidean space, upper and lower indices give the same value. But we use upper indices here to apply Einstein's summation convention. Also, an strictly represents components, but as shown above, it can be regarded as a vector. In curved two-dimensional spherical coordinates, the vector is expressed as More precisely, x is shorthand for x mu, that is, x1, x2, or theta, phi, but here we use x to emphasize the location. Regarding the relationship between an of n and a of x, since the spherical coordinates are embedded in three-dimensional Euclidean space, this point is exactly the same point in both coordinate systems. Therefore, this expression rewrites the vector in flat Euclidean space in terms of the curved surface coordinates. We now parallel transport the vector an of x at point x to a nearby point x plus dx. As shown in the figure, the vector an of x sticks out of the two-dimensional curved surface. We therefore project the parallel transported vector an of x onto the two-dimensional sphere at point x plus dx. The projected equation becomes an tangent is tangent to the curved surface. Of these, only an tangent lies within the two-dimensional curved surface at point x plus dx. Just as in equation 1, we rewrite an tangent in terms of the curved surface coordinates. Note that partial yn over partial x mu represents the basis vectors at the point x plus dx. Since an normal is orthogonal to an tangent, we can express this orthogonality condition using the inner product. To do so, we lower the index of an tangent by contracting with g and m to obtain the covariant form. Relabeling the dummy indices. Swapping n and m, we have an tangent and an normal are orthogonal, so their inner product vanishes. By lowering the index of an tangent, we obtain a paired upper and lower index, allowing us to take the inner product. Since mu is defined on the tangent space and an normal is normal to the surface, they do not couple directly. Now that we have everything in place, we return to equation 2 to complete the vector at point x plus dx on the two-dimensional sphere. We multiply both sides by partial yn over partial x mu to eliminate an normal. Substituting equations 3 and 4 into this. The product of the partial derivatives on the right-hand side is the metric. So we substitute. Swapping the left and right sides. Note that partial yn over partial x nu are the basis vectors. Let's Taylor expand this and express it in terms of the basis at point x. Substituting this into equation 5. Using equation 1. We express an of x in surface coordinates. Since g mu nu is given by this a nu of x plus dx represents the vector a nu of x, parallel transported to point x plus dx. The difference between the component a nu of x at point x and the projected component a nu of x plus dx after parallel transport to x plus dx is given by this represents the change in components under parallel transport. However, since the vector itself is invariant, this is purely an apparent change due to the difference in coordinate systems. Christoffel symbols. We have derived the equation of parallel transport for a two-dimensional sphere embedded in three-dimensional Euclidean space. However, this was obtained from one dimension above. In this expression, yn, here we still have traces of the n-dimensional, in this case three-dimensional, embedding space. Our goal is to derive the equation of parallel transport using only the coordinates of the two-dimensional sphere itself. For example, we are three-dimensional beings, but we want to discuss geometry using our own three-dimensional coordinates, not four-dimensional coordinates from one dimension above. Let's find a way to replace the n indices here with coordinates on the surface itself. Our goal: eliminate the n coordinates and express everything in terms of the curved space coordinates. Since the metric is given by this expression, let's differentiate it with respect to x sigma. The term we're looking for has appeared. In equation 1, we exchange mu and sigma. In equation 1, we exchange nu and sigma. Taking the combination 1 plus 3 minus 2. The left-hand side is called the Christoffel symbol of the first kind and is written as. Therefore, equation becomes. We have derived the equation of parallel transport in two-dimensional spherical coordinates. The Christoffel symbol that appeared is composed entirely of the metric. Recalling the line element. This holds for all coordinate systems, whether two-dimensional, three-dimensional, or n-dimensional, and whether the space is flat or curved. Therefore, the equation of parallel transport we derived is also applicable in all coordinate systems. Now to express the change in a vector under parallel transport, we no longer need to refer to the n-dimensional space. In other words, we can now express everything using only the coordinates of the space we live in.